Now, our next talk is entitled Program Sketching with Live Bidirectional Evaluation. Justin Lubin will present the talk and he will introduce Smith, an example-based program synthesizer with support for sketching and no trace completeness requirement.
Hi everyone, my name is Justin Lubin, and I'm going to be presenting program sketching with live bidirectional evaluation. So this is a program synthesis project, and by program synthesis, I mean computer generation of programs satisfying a specification. So the two key words to take away here are satisfying and specification. So let's take a look at what I mean by those. By specification, I mean the user interface to a synthesizer. It's how the user provides a notion of correctness for a potential program. Satisfaction is then simply a program meeting these specification criteria. So let's take a look at two popular user interfaces to synthesizers, the first of which is logic-based synthesis. In logic-based synthesis, we provide a logical formula as a means of specification. So for example, if we're trying to specify the sort function, we might say that for all indices I in an array A of I has to be less than or equal to A of I plus 1. Satisfaction in logic-based synthesis is typically going to be static verification. So for example, we might use tools such as SMT solvers, dependent type checking, model checking, etc. Now, there have been many great logic-based synthesizers that have come out over the years. For example, Synquid, Rosette, Sketch, and Leon. These types of tools excel when we need to encode complex invariants about more complicated data structures, such as red-black trees. Let's take a look at another interface to program synthesis, example-based synthesis. In example-based synthesis, specification takes the form of input-output examples. Here, I've asserted that sort of the empty list is the empty list, and that sort of 312 is 123. Satisfaction will now take on the form of dynamic verification. So what we'll need to do is we'll need to test each input-output pair. We'll need to evaluate and check. And the keywords on this slide are evaluate and check. We'll definitely be returning to that later. So some really great example-based synthesizers that have come out include Myth, Escher, and Lambda Squared. For this project, we're going to be working in the domain of example-based, richly typed, general-purpose, functional program synthesis. Let's take a look at the current state of the art in this domain to see what we're up against, and that would be the Myth project. The way that Myth works is you give it a type signature and a set of input-output examples, and as output, you get a function that, when run, will satisfy those assertions. For the purposes of this talk, I'm more or less going to be treating Myth as a black box, one that will take in examples and give us a solution as output. Myth is a powerful program synthesizer, but it has two key limitations that we might like to address. Let's take a look at the first of these two. Given input-output examples, Myth will transform an empty program into a full solution. But what if we, as programmers, wanted to encode some domain-specific knowledge that we might have into a partial solution towards the program that we'd like to make? Then we'd like for Myth to transform this partial solution into a full solution. The idea here is known as program sketching, and it already exists for logic-based synthesis in untyped languages via the Sketch and Rosette projects, but we want sketching for example-based synthesis in a richly typed language. So to recap, program sketching is when you have a program with some holes in it, which might possibly be interdependent, and arbitrary assertions on this program, which is where we're going to derive our input-output examples, and what you get at the end of the day is a completed program. So let's take a look at Myth's second limitation, which is known as the trace completeness requirement. To be fair, this isn't just Myth that suffers from this problem. A lot of the program synthesizers that I mentioned earlier also have some sort of trace completeness requirement. So what is trace completeness? Well, a set of examples for a function is trace complete if, when the function is called on each example in the set, all its recursive calls also have an example in the set. Let's take a look at a small example. Let's say I have the length function as defined here, and I want to specify the example that length of 1561 is 4. Well, the problem is that length actually makes a recursive call here on the tail of its input. So I'm going to actually need to specify an example for length of 561. And similarly, I'm then going to need to specify an example for length of 61, and length of 1, and length of the empty list. So to recap, here are two limitations of Myth. First one is that it has no support for sketching, and the second is that it has this trace completeness requirement. But instead of framing these as limitations, what if we treated them as goals, and instead of saying that there was no support for sketching, we wanted to add support for sketching and remove the trace completeness requirement? Then we could call our system Smith. So what we'd like to do is provide Smith a sketch, which would be our first goal, and some non-trace complete examples, which would be our second goal, and get the same output as before. Let's take a look at how we can support this first goal, adding support for sketching. So here's how Smith is going to work. As a specification, we're going to give it a sketch and some assertions. And because Smith is example-based, we're going to need to do dynamic verification. As before, this means that we're going to need to test each assertion. We're going to evaluate and check. But here's where it gets tricky. What exactly do evaluating and checking mean when given a program sketch? Well, the answer to the first of these questions is live evaluation, which is theory that we draw from the Hazel project, which you can find at hazel.org. Let's take a look at how it works. Say we're given the program E on the left, which computes 10 plus 20 plus the first of this pair x, where x is 4, comma, a whole. Well, we can compute the 10 plus 20 and get 30 just fine, and then we can also take the first of this pair, which we know is going to be the concrete value 4. So we can get normal output, 34. Notationally, we would say that in the empty environment, E evaluates to 34. But what if we change the first of x to second of x? We can compute the 10 plus 20 just fine as before, but now second of x is going to give us a whole. In traditional programming systems, this would either result in an exception or a crash or some sort of meaningless output. But the key inside of live evaluation is that we can actually just evaluate around this hole. So because we have a hole in our input, we'll get a hole in our output, and we get 30 plus hole 0. Note that we also keep track of the environment around the hole at the time of evaluation, because that's going to be really useful for synthesis later. Notationally, we would say that in the empty environment, E live evaluates to 30 plus hole 0 with that environment. So that's how we can run these program sketches. But now how do we check these program sketches against the arbitrary assertions that we might have on them? Our answer to that is a novel mechanism that we call live unevaluation. Let's take a look at how live unevaluation works. Let's say we're given the same program before, E, and it evaluates to 30 plus that hole closure, hole 0. Well, if we want the entire program to be equal to 100, then we can actually transform this global constraint from an assertion onto a local constraint on the hole, namely that hole 0 needs to be 70. As a slightly more complicated example, let's say we have a program E that evaluates the first of some hole, hole 1, and we want the entire program to evaluate to 8. We can transform this global constraint onto a local constraint on the hole, namely that hole 1 needs to be the pair 8, comma, top, where top is anything at all. Finally, let's take a look at our max program from before. If we want to assert that max of 1, 2 needs to be 2 with this program sketch, we can actually live evaluate it. So in the empty environment, we say that max 1, 2 live evaluates to hole 2 with the environment n equals 1, n equals 2, n prime equals 0. We live unevaluate the 2 onto this expression, and we get the whole constraint that hole 2 needs to be 2 in that environment that I mentioned earlier. So that's how live unevaluation works. Thus, satisfaction in Smith will look like live evaluation followed by live unevaluation. And it's the combination of these two concepts that we call live bidirectional evaluation. But as a satisfaction mechanism, live bidirectional evaluation actually introduces these new constraints x over here on the right-hand side. So let's take a look at a high level how this will fit into the program synthesis loop. In Smith, we're going to start with myth as a black box. Then, when the user provides a sketch, we can live evaluate it and get a result. We'll also collect these program examples from the assertion and live unevaluate them onto the result that we get. This process, which we call live bidirectional evaluation, will result on constraints on individual holes that we can plug directly into myth. Then, if we augment myth with some additional rules to handle the partial solutions that we're looking for, we can actually get a partial solution from myth and some new program examples. Then, we can iterate this process until we arrive at a full solution. So, if we look back at our goals, we can see that live bidirectional evaluation enables us to add support for sketching. What about this trace completeness requirement? Well, it turns out that live bidirectional evaluation also solves this problem. To see how, let's take a closer look at trace completeness. Let's say we want to specify the function length using these two non-trace complete examples, as well as a blank sketch. The first step would be to live unevaluate these assertions and get the two hole constraints that when x is the empty list, hole 0 needs to be 0, and when x is 1, 5, 6, 1, hole 0 needs to be 4. Because Smith is not going to find a non-branching expression to satisfy this hole, it's going to introduce a case expression that splits on x's. Now, we'll live unevaluate these assertions again and get two new hole constraints, namely that when x is the empty list, hole 1 needs to be 0, and when tail is 5, 6, 1, among other things in the environment, hole 2 needs to be 4. Now, this first hole constraint is very easy for Smith to solve. It can simply bind hole 1 to be the constant 0. That'll take care of this first constraint, so we no longer need to worry about it. The second constraint could be handled similarly, but Smith avoids overspecializing on large constants like 4 because they don't generalize well. So instead, it might try to synthesize the expression 1 plus length tail. But we run into a dilemma here. How can we be calling length on tail when we don't even know what length is, because that's the function that we're trying to synthesize in the first place? Here's where traditional program synthesizers could leverage the trace completeness requirement. If we were guaranteed to have the example that when x's is equal to 561, length of x's is going to be 3, then we could simply slot in 3 for length of tail and see that 1 plus 3 is going to satisfy our requirement that hole 2 needs to be equal to 4. But we don't have that example. So instead, the key insight is to realize that we actually do have a definition for length of x's. Length of x's is going to be equal to hole 0. In our partial solution, we see that hole 0 is going to be equal to this Cache expression right here, which depends on hole 1 and hole 2. But nonetheless, we can run live bidirectional evaluation from before as usual on these programs because they're just normal sketches. Doing so will result in a new set of live unevaluation problems that we can just perform to get a set of new constraints. And it turns out that this program that we synthesized actually satisfies all of these generated constraints, as well as our original constraint that hole 2 needs to be 4. Therefore, all of our constraints have been taken care of, so we have a full solution for length. So that's how live bidirectional evaluation can also take care of the trace completeness requirement from Myth. So to wrap up, let's talk about some of the experiments that we ran to evaluate Smith. Here I'll be talking about 4 experiments that we ran based on the Myth benchmark suite. In the first experiment, we took the trace complete examples from the Myth benchmark suite that specified various functions and provided no additional sketching information to Smith. With this information, we could successfully synthesize 38 out of the 43 benchmarks from the Myth benchmark suite. In the paper, we talk about some hypotheses why we couldn't get that number up to 43. In our second experiment, we took these trace complete examples, but we removed as many as we could while still having Smith synthesize a correct solution. We found that with these non-trace complete examples, we could achieve a 61% specification size in Smith as compared to Myth. In our third experiment, we took just the recursive functions from the 38 that we could synthesize and provided a sketch of the base case to Smith. Then, like in experiment 2, we took the trace complete examples from experiment 1 and pared them down to a minimal subset that Smith needed to be able to synthesize the function correctly. Including the sketch of the base case, we found that we needed approximately a 46% specification size as compared to Myth. In our fourth experiment, we ran experiments 2 and 3 in the popular logic-based synthesizers Leon and Synquid. It's commonly said that logic-based synthesizers are strictly superior to example-based synthesizers because you can simply encode examples in logic as a conjunction of implications. While there is some truth to that sentiment, it's also true that many logic-based synthesizers are not well equipped to handle that kind of specification. And in fact, this experiment showed that while there were many tasks on which Leon and Synquid performed quite well, there were also many tasks on which they did not, particularly relating to non-trace complete examples. We hypothesized that combining the insights of live bidirectional evaluation with logic-based program synthesis could result in a system that has the power to specify complex data structure invariants while also having the ease of use of not having to specify trace complete examples. The last thing that I'd like to say is that these 4 experiments are a measure of expressivity, but we also ran experiments that tested the robustness of Smith, and these are described more in the paper. So that's Smith, an example-based program synthesizer with support for sketching and no trace completeness requirement. Here's an overview of what the system looks like, and here's a link to where you can find it on GitHub. You can also find me at jplubin on Twitter. I'd like to give a huge thanks to my collaborators Nick Collins, Cyrus Omar, and Ravi Chugh for helping me with this project, as well as the ICFP organizers and volunteers for making this conference possible. Lastly, I'd like to give a shout out to an event that I'm helping organize at ICFP, #ShutdownPL at ICFP. It'll be an anti-racism event occurring on Thursday, August 27th from 2 p.m. to 6 p.m. Eastern Time. I hope to see you there, and thanks for watching.
Thank you, Justin. And thanks a lot for organizing the anti-racism event, #ShutdownPL at ICFP. If you're watching this talk live, please don't forget about a Q&A session that may be available in your time band.